Okay, so the first thing, once again, will be on page 6 and 7. If you weren't here, just turn around or grab someone to take a picture of their data, and then you can make the graph too. All right, so this is a review. We'll give you a few minutes. So what's it? Oh, probably right for that picture. I'm sorry.
It's all, I think it's
All right. So I feel that way.
it's good.
Graph should look something like this. And here, someone's talking. All right, then it should have 2 lines. You don't have colors, but that's okay. You can just do it like you did. And one would be like the height of your reactants. And one would be the height of your products. So in your data tables, the top row says trial number, it goes from 0 to 20. And then your data is underneath those. So you'll have centimeter of reactants, centimeter of foam. So you'll have, let's see, but it won't look like this because I don't want to tell you the answer. It'll look something like this and this. All right? That shape is absolutely wrong, but I don't want you to just copy what I write. So just trial number on the bottom. You can put the height, whatever that should say height of your reactants and products, and I'll just let you go. Maybe about 5 minutes. I'll do a check at 5 minutes to see how we go. So let's talk about these graphs. The first one, we just put them all in the same number. Graph number 1. No. Is that right? Okay, first graph should go something like this. Second graph should go something like this. Second line should go something like that. Is that okay? Okay. I already forgot I was going to put them all 3 on the same slide. All right, so there's graph number 1. Yeah. Which is one thing is similar, but mostly it's different. Those should be flat. And number 3. It should be the same pretty much. Something like that. Now, a lot of you, graphs don't have a curve at the start because you started it already at equilibrium. So if your graph looks just like this, I mean, it's boring, but it's acceptable. All right, this is what I'd like you to do. If you haven't drawn graph number 3, do it as fast as you can. Then on graph number 1, I want you to circle where equilibrium is. And I'm going to walk around and see if you circled the right part. So circle where equilibrium is represented on the graph. Whoa. Can you get the graph copied? Well, I don't know what I've done to it. No one so far has circled the wrong answer. Usually, tons of kids circle the wrong. All right, well, let's play like wrong answer, Jeffrey. What do kids normally that get it wrong circle? Any guesses? Right, when they cross. And that is incorrect, but all of you, first and second hour so far, have circled this area. Now, you can circle just one. You can circle like just a point when it's flat, but it's this whole thing, wherever it's, when they're flat and parallel, that's your equilibrium point. Now, super simple idea here. What happened when we did this lab is we had a little of this, a lot of that. This top one, that was the 250 milliliter. The bottom one, switch U times A. All right, the bottom one here in red, that would have been the 150. And the fullness of 250 decreased over time, and the 150 stayed the same, and eventually it became equal. So we have the all right. So make sure on a graph, because there's two of these questions on the exam that are really, really simple. What's that? What do you want to talk to? They're on, oh no, they're not on the test. Those, they don't match those. Here's what they are. They're from the graph. It says, it'll give you a graph like this, already drawn, but it also has like the graduations. Let's say this is like 4. The question on the test will say, what day does this reaction reach equilibrium? So you would look up to where they finally go parallel, whatever, day 4. On the test, it's really obvious. That's all you have to do to answer that question. You look for when they start to go parallel. And then the other question on the test from the graph, give you this graph, and it says, what will be the concentration of the red line at day 10? Tell your partner what you think that will be. Now, I know you don't have a number over it, but tell your partner, what's the way you could answer that with just this graph? Whoa. You knocked that out of the park. Say it again louder. The same as day 4. Because this line, I won't draw it very well, but it will stay the same forever. Whatever day 200 is, if it's at equilibrium, it's still the same as day 4, or the day it went to equilibrium. Are we okay with that? They're two super simple questions, but they're worth 5% of the test. So that's an easy 5%, hopefully. So we look for when they go flat, and then the answer here is the same as whatever day they are. Okay, now let's talk about the questions at the bottom. What are our answers there? We may have talked a little bit about a couple of them. By the way, if you were anyone that sent these girls, they really bloomed over the weekend, much like me and my teen years. Well, don't laugh at all. Sorry, I try to be funny sometimes. I'll be more boring. I'll be like Peter Bird. All right. I was gonna be like Peter Bird. I'm not excited enough that I don't like big enough. That's being recorded. Sorry, online students. Okay. The 3 questions at the bottom, actually there's 4. Number 1, someone read that out loud for me. And you win the literal award of the year. Don't read this to me. Someone read question number 1 on the bottom of the page, whatever we're on.
In the experiment, what represents reaction rate?
All right, so what determined how fast the water was transferred? The full of gotta know by now. Beaker, thank you. The fullness of the beaker. It's how the trick works. You get your big can, or so you can, with your big beaker, suddenly it won't fill up all the way. Like you tip it and your 250 only fills to here. All right, then you have your can over here with more water, you dump it in, and then you take your little one and you fill it all the way up, pull it out. At equilibrium, this is roughly 150 milliliters, and this is roughly 150 milliliters. So the rate of my forward, going this way, and my rate of reverse are equal. Okay, that's the whole trick. The amount of reactants, this is the first, the amount of reactants got so low, the rate slowed, or the fullness of the beaker. Okay, question number 2. What does that one say?
What happens to the fullness of the large
Oh,
in the can, which is
thank you. I believe I just answered that one.
Yeah.
Did anyone hear the answers? I said that. I'll leave that one up to you. Thank you. Okay, now, number 3. I already know what that says. It says, what is true about reaction rates at equilibrium? Is that about right? Okay, I want you to answer that, and then I'm going to walk around and see if you have the right answer. This one's just it's an important part here. It's the whole point, really. So write your answer. In my opinion, you can answer it in 3 words. So number 3, what is true about equilibrium? Of reaction rates at equilibrium. Give me a second. I'm sorry. Woo. That was a beautiful answer too. Yeah, you gotta go to the bathroom? Are you gonna come back? All right, we'll see you in a little bit. All right, so 2 for 2 over here. 3 for 3. I can read it, but. All right, I heard the word same. No answer yet. Buzz, yes, when I walk around. Very intimidating. I consider getting uglier just so I'm less intimidating. What are you arguing about? What's wrong with that? Oh, no. Tyler, I waved you to the driver's ed. I rolled down the window and said, hey, Tyler, when you were trying to light something on fire in the garbage can yesterday, that didn't look creepy at all, by the way. So 9 2. Okay. But remember, you got mad at me last time, so I went out of my way. It looked like you were trying to light a piece of paper on fire in the garbage can. It's probably a love note from an ex-girlfriend. You didn't want your current girlfriend to find it. I understand. Moving on. Okay, almost everyone I saw wrote similar things, and they put that they or they are the same, or you're up with forward and reverse reaction rates are the same. Most of you put that just fine. Okay, number 4, that's a thinker question. I'll let you try and figure that out. I'll give you 30 seconds. Write your best guess. If you're wrong, we can still be friends. We're not even going to talk about it. Just try it. right, that was a very long 30 seconds. It was like 32 seconds. All right, hope you feel all right with that. The answer is something like that. Okay, now, okay. And 9, it is the causes of stress. I know. They had a news article last night on the national news that kids in 2020 are more stressed than they ever have. Now, I don't know why, how on earth do people make money researching the obvious? It's like saying, I'm gonna go out and study if there's more snow, if it's snowing. Oh, it turns out that there is. Anyway, you know you're stressed. I promise we want the best for you. Just keep it up. Okay, now this is the little asterisk here because we're talking about in chemistry, and that doesn't mean chemistry test. That means we're talking about what we call Le Chatelier's principle. It really does apply to life. So, whatever, we'll just jump in. So, there are 3 main types of stress when we talk about chemistry. And one is when we change the concentration. So, changing the amount of any reactant or product in a system at equilibrium disturbs the equilibrium. Okay, so what we're talking about, if I have sulfur and oxygen, and they are in a dynamic equilibrium, and they form SO2. We'll keep it simple, so it's just a 1, a 1, and a 1. All right, and we know it's an equilibrium, and we can graph it, something like this. And like it's an equilibrium right here. So what this is saying is, let's say this is S, and this is my SO2. What I'm saying is I'm at equilibrium, but now I'm going to change the amount of one of the things. So I come along and I add sulfur. You'll get a spike right here because I, Tom Davidson, the scientist, put sulfur into the system. So what happens? Sulfur will start to react with oxygen. So I put it in, and it starts to react with oxygen to form SO2, so its concentration comes down. All right, and it goes flat. Well, let's think about what probably happened to oxygen. If I add S to make this, what's going to happen to the amount of O2 present? It's going to go down. And then we establish another equilibrium position. And these equilibrium, they'll be flat again, but they'll be at different points on the graph. Now that's complicated. That's what we're saying. If I have a system at equilibrium and I add or subtract an amount of reactant or product, it will disturb the equilibrium. Okay, here we go. Adding a chemical pushes the equilibrium position towards the opposite side of the arrow. All right, so let's pretend we have this simple equation in our life. I have money, which I use to buy stuff. I can do that. I do that all the time. I take my money and use it to buy stuff. So let's think about it. If I got more money, what am I probably going to do? I'm going to buy more stuff until I reach a new equilibrium. Because as I start spending money, I don't have as much as I used to, but I have more stuff. Right? And now I have a new equilibrium. So chemistry is the same. If I add more things, I make more stuff. Okay, now let's say there's some bad things happened, and I lost a lot of my income. So I took away my money what am I gonna do to my stuff? I'm not gonna have it. I'm gonna have to sell it, or the bank's gonna take it from me. So, so I start selling it. When I sell it, what happens to my money? It starts coming a little bit back. Until I reach the equilibrium. Okay? Chemistry is the same. If I add stuff, I get more of the other side of the arrow. If I don't know who drew that, I don't remember. It was a great job. Ooh, I'm gonna stick you out over there. All right, if I remove the chemical, it pulls the equilibrium position towards the same side of the arrow. Okay, so there's two phrases I want you to kind of remember. They are take, I, stay. And then the first one was if you put in that order, like add, away, take, I, stay. Okay, I have now 4 very simple demonstrations that I'll do up front. They really teach what we're after, and they don't really require a whole lot of effort or chemicals, even brain power. That would usually take out. All right. Did I use this and all the other day? Yep. Okay, so I'm going to use it again. This thing is a perfect example and application of the Chatelier's principle. So I'm just going to add some food coloring here, just so it's easy to see. And we have a chemical reaction that's about to take place. I need reactants in order for a reaction to happen. Oh, I need to turn the camera on. Hold on. Switch this. When I go back to teaching up here, someone's got to remind me. So I'm just switch it back. Okay. It seems just a little tight because I have to suck in a lot. So let me back that out a little. Okay, here we go. So what I have these two 2-liter things connected with a little milking hose. That's what I use it. There's, all right, I'm gonna add reactants. Once I get a high enough concentration of reactants, the reaction starts, and I start to produce products. Now I'm gonna add a little more. So I can get it to reach a state of equilibrium. Tell your partner real fast what you think equilibrium will look like. Feel free to make noise. All right. So Ian's saying the same rate of transfer. That's the nerd answer. Nothing you can see, like that's a great answer, but that's not what it looks like. What does this look like in equilibrium? That's right. There's not 4 down, right? The amount of water, or the height, I should say, not the amount. The height of the water is not changing. Fair enough. So we are at equilibrium. So if I had that graph up still, it would be level. Okay, don't do what I want you to do. And still don't. Here we go. Let's go what you need. Okay.
You need to switch to the screen.
I'll be all right.
Okay.
Personal line, pretend like you're looking at the graph. I just put them off. I apologize. Megan, don't shut them off. Anyway, our graph, we're at the flat part. So online, you don't need to just imagine the graphs we drew, they are now completely flat. So they're equilibrium. All right, now I'm going to change the concentration of reactants. So do you see where it says 1, 2, 3, 4? With me, thumbs up. Okay, so the first one says, what was the stress? So if you look at me for a second, the stress I'm going to apply is I'm going to add more reactants. So go ahead and write that for number 1. And then I'll add reactants, but I'm going to keep my hand over here so nothing happens yet. a scientist. The reaction didn't add reactants, I did. You okay with that? So the stress was I added reactants. It doesn't take rocket science. Tell your partner, what will this water do to fix the equilibrium? It will produce more of what? Okay, when I remove my hands, it makes more products. Okay? Not that hard. Okay, so if I add to one side, it always goes where? The other side. I know it's in red, you can't read it very well, but this says right here. Adding a chemical pushes it to the opposite side. Or a shorter way to say that is add, I go away. Add, I go away. If I add more water to one side, I move back to the other. Okay, stress number 2 in the demos, the 1, 2, 3, 4 on page number whatever. The second stress, I'm going to add products. Because remember, this is a reversible reaction. All right, so I add, like, max my products out. It's not the hardest science ever. What will happen as soon as I remove my hand? What direction will it flow? Towards the reactants. So it doesn't want to be out of balance. It wants to get back to an equilibrium. You okay with that? Okay, so both of those, if I add to one side, I move to the opposite side. Yeah, we also did have the second slide though. That said, if I remove, I pull it towards the same side of the arrow. So this one's harder to do. Be without a map for a few minutes, don't judge me. I can't just pour one side out, so I'm going to blow the force water out. So here we go. Okay. So now we're pretending I removed products. So that's your stress on number 3. I removed products. Once again, not super hard. Where is the water going to flow? It's going to flow from where to where? Tell your partner. All right, so we go from the reactants to the products. All right. So whatever side I removed from, it flows right back to that same side. You're not actually in this class. All right. End of period. Okay. Pretty close. Okay, so I removed products and came back towards the products. Say that. Okay, the last one, I gotta be careful, so I'm going to remove reactant. All right, so now I remove reactants. Very simple. What direction is the water going to flow? Towards the reactants. So when I add, I go away. But when I take away, I stay on the same side of it. Do we remember? Share screen. Remember our awesome analogy of digging a hole in the sand or making a pile of sand? Does that sound familiar? Yeah. Talk about that. This same stuff works. So here I am on just loving life. We'll go to this slide. I just can't believe that. Like it's too pretty. Someone put effort in someday. So I go back to this slide real fast, and then we're adding. So like we got our pile of sand, and then I add sand to the top. Where's the sand really going to go? It's going to go away from where I just added. Because that's just how sand works. It's rude. All right, so if I add and move away, finish the same. Okay, then what if the hole is there? And I take my shovel, that's supposed to be a little deeper in the hole, but whatever, and I take some sand out, I remove. What happens? The sand falls right back to the same place. And away. Okay, I stay. So let's apply this now to some homework problems. If you'll turn to probably page 11, hopefully. Is this on page 11?
Yeah.
Okay. So it's problems 18, 19, 20, 21. So what we'll do is we'll do this every single time the same way. You'll never get them wrong. Please remember, add, away, take, stay. Just apply it. So this top one's an example. It says, now on your homework, the word added is right above here. So all of these are added. So every single one of them, I go away. So what it says, circle the reagent changed and then use add away take estimate. So it tells me the reagent is CO. So I'm going to come over to reaction, I'm going to circle it. And then if I add, I go away from it. So what that means is I'm moving towards the opposite side, which means the equilibrium shifts towards the product. So let's look at number 18. I have hydrogen, so I circle hydrogen. I add it, so I move away from that side. So number 18, I move towards which groups? The reactants. So we try 19, 20, and 21. These are too long. Make sure you see the exact formula. So this says O2. That does not mean SO2, it means just O2. So, with the CO2, I go away, that moves towards reactants. If it's SO2, I move away, I go towards the products. If it's O2, I add, I move away, that's towards the products. You got that so far? You have to do that on the test. Hopefully, it goes pretty quick, pretty easy. So tomorrow, we'll go to the other two, they don't take very long, and then we'll review. The test is Thursday. All right. Have a good day, all liners. Wish you were here for this